Hi guys, today will be the final one with this Chinese New Year holidays. We're going to talk about complex ions. There'll be about 2 or 3 more left, but today I'll talk about stability constants here. Last bit here, right? Okay, last bit here. Stability constant is called Kstab, K-S-T-A-B, or stability lah. Okay, right? Someone asks you the meaning of K-stability. Let's read through these things here first. Describe and explain ligand exchanges. Now the reaction is called ligand exchange. Okay, if I ask you what kind of reaction is this, it's called ligand exchange. It's the most popularly used term. Ligand exchange or ligand displacement. Okay, there are a couple of names given for this reaction. It's called a reaction. Okay. Right, ligand exchange is the most popular, or displacement, or replacement. Okay, where one ligand kicks out another ligand because of more stability. Okay, for completing equilibria, that means it's going to be reversible. State the stability constant Kst. Now, Kst is used. Remember, is a equilibria. That means it can go forward and backwards. Okay, for a complex ion in the equilibrium constant. For formation of complex in the solvent constant of ions and molecules. So we look at the formation of a few types of complexes. And remember, you always compete with one common complex, which is the water ligands. After I'm show you, okay? Use expression for stability constant for ligands. Okay, expression same old thing on Kstab. Okay, ligand explain ligand exchange. See, they use the word ligand exchange here. So the word exchange here is most often used to ask you what kind of reaction is it? Ligand exchange. Easiest, okay? Right? Now, okay, stable and so forth. Now let's go straight to the notes. Right, I'm going to go to theory first, then look at the questions. Then we finish. Okay? All right, so the 28. Okay, formation and stability of complex ion. Okay, ligand exchange. Remember, I put down here again, ligand exchange in complex ion. Remember, there's already a complex ion, right? The complex ion consists of what? A central ion or atom. And of course, there are ligands around here, right? For example, NH3. Okay, 4. This is the ligand. Okay, this whole thing is called a complex. Okay, so they're going to be exchanged. This will come out, something's going to go in. Okay, maybe CH3 and H4. CH3 going inside. So coming in and going out is called ligand exchange. Stability constant definition, it is the equilibrium constant, but it's actually a Kc. Okay, applied to the formation of complex ion. If they ask you what do you mean by stability constant? It is the equilibrium constant. So it's called K, right? K. Big K. So big K is only applied to when there is an equilibrium. Okay? So equilibrium constant applied for the formation of a complex ion. This is very important. Form is aqueous complex. Always refer back to the water complex. For example, here. Right? Now, I will go through this more with you for copper chemistry later. Okay, it's hard to jump here and there, so I go according to the syllabus. Okay, now this is your blue copper sulfate solution or whatever copper chloride solution. Now this is, of course, the ion. This is the copper hexa. Remember, this one is like that. If you remember, Cu2 plus here and Cl. Sorry. Water here, water here, water here. There's 6 of them. Some books put 4, the one. Follow Cambridge. Okay, now 6 of them here. So this is the blue color. This is the aqueous solution, like copper sulfate blue color. This is the one. So this is the starting point of all complexes which is being exchanged. So I put this from concentrated HCl. Okay, high concentrate. I put inside here, step by step, the water here, the water will be exchanged. This is blue. Right, an exchange here is no longer a octahedral. yeah. They will change to a yellowish green. Actually, it's yellow color. Yellow, okay? Into a tetrahedral. Remember I told you CCCC, copper chloride, cobalt chloride, chromium chloride. All of them are tetrahedral. Okay? Copper, cobalt are +2, chromium is +3. They are all tetrahedral. Okay? So because of they say the large size of the Cr minus and the charge, so they repel each other, they can't go near 100. They can't go near 90, they have to go 109.2. Okay, now in this case here, because it is actually reversible, you can do actually reversible. You put water, now actually this one is over here, okay, because of typing I cannot, okay. So if you go to this, which is yellow color, if you put water on this side, it will go back to the light blue one. For example, you can see here, there is a diagram to show you the color, okay. Okay, now here. See, remember this is reversible, okay? So if I put in here corn HCl, right, it will give me this color which is yellow, okay? Yellow in color, no? Right. But of course, some blue will remain. That's why some say yellow green. That's blue and yellow give green, no? Yellow color. So if I put into here water, right, you go back to here. Okay, so it's reversible. This is a reversible reaction. Okay, I can see here. Right, this is the first one here. Okay, all right. So let's go back to here. So now this is, then you will be asked to give the expression of this one here. So this expression KST or KS step now. Okay, okay. So remember, right? It's a ratio of the products, isn't it? Right. So here, now the water, right? Actually got 6 water here one. But water is not included. Right? Don't put the water there because it's such a large amount that you don't include water. Okay, so no water. Huh? So don't put water, don't put water. Remember, it's too large amount, so it's a constant here. Okay, so this is the product. Power, this one is your here, power 1. This one here, so this one here, so it's power 1 here. This whole thing can put aqueous here. Doesn't matter. Can put water, doesn't matter, right? Power 1, that's power 1 here. And Cr minus 4 here. So remember this thing will cancel off. And this one here, the units cancel. They ask you for units, so it's 4. I'll bring up here. So more 4 and 12. The end. Okay, now. So now the size of this value here, well, will tell you how stable the product is. This product is. The bigger the value, the more stable. It means that you shift to completion. Completion. So what happens is that the ligand replaces or exchanges the water ligand. Okay, so it's called a ligand exchange reaction. Ligand exchange. I give it the most popular term, reaction. All right. Remember, you can say ligand replacement reaction, ligand displacement reaction. They all give mark, but I try to use the most popular one. So we say the ligand here or Cr minus is stronger than water. So it kicks the blood out. Okay. Now here the couple of stability constants are normally very large. So the log is being used. So log KST here. So instead of 1.12, 13, put 13.8. Okay. So this is a better way to explain. So what does the stability constant depend on? So here depends on the central metal ion or polarizing power. They will pull the ligand stronger. Of course, Fe3 plus 2 plus here about the same radius, but it's 3 plus no. So of course it will form with the same ligand, Cr minus. Remember Cr minus is this one, okay? Right? So it's 1, 2, 3, 4. And there's one here from somewhere, don't care where it's negative here. You also got here cross. It's 7, yeah? But this is the one that will form the bond. Okay? So the carbon that will form the dative bond with the central ion here. Okay? So here is 31. So bigger than, stronger than, right? So the strength, the largeness of the KST depends on, if the ligands are the same, depends on the central ion or atom, which has large polarizing power. Now, across the period from manganese to copper, of course, you can see here, right? Manganese, iron, cobalt, nickel, copper. Of course, if you look at the data booklet, you see manganese is from here. It's from here. Okay, manganese to here. Okay, of course, you can see if you compare, they're all same charges. Of course, the same charges, but the number of protons will be increasing, isn't it? Right? So you can see here, right? The same charges, manganese to copper, last one is +2, +2 are quite stable, right? +2, but because as you go across here, even though it's +2, right? The number of protons is increasing, right? The charge is, the radius is also decreases a bit. So now they're the same En, or same En. Okay, so increase in charge density, nuclear charge increases. Okay, right? The number of protons increases, smaller and invariant radius, or so the pool of the towards the common En. Remember, En is your this one here, NH2, CH2, CH2, and NH2. Right? Okay, the pool is stronger. You can see the value increases. Okay. So the second one, of course, is polydentate, right? Monodentate, bidentate, and polydentate. Okay, so you can see that there's a increase. Okay, this one, of course, it is 6. No, one molecule can get 6. Right? Hexadentate. So this is strongest EDTA. Okay, so they can replace each other as after you see here. Okay, right? Now you can see EDTA here. One year they came out, I think I forgot where is it. They draw this for you and say, well, name the parts of the, or circle the donor atoms. Remember, it's always the O negative. Okay, you got 6 electrons here. So 2 before for bonded, 6 free, 6 or 3 pairs. Okay, for nitrogen, there's one pair. So, okay, so these are bonding nicely, fit. Fantastic fit in nature. You say nature, God is fantastic. Okay, so here we got it. You can read it up for yourself if you want to. The uses of polydentate. Okay, now here. So got copper. Copper is famous. Now they give you here 2 KSTs, right? 2 K stabilities, one for copper tetraamine. Of course, I left out the water here. Okay, right now there are 2 water here. It's not to have. Okay. So 2 here, I can see from here the value 13 and 5, right? So this, now remember this value is compared to water like here. The question is, what will happen if ammonia solution is dropped to a copper tetrachloride? The mid starting point here. Okay, so I do in class, I can see very clearly. Okay, let's say we start with copper 2 plus first. Okay, which is a copper H2O 6 2 plus, and you put in HCl, corn HCl. You will see the first will change. The blue color, this blue color will change to orange. Oh, sorry, green. Sorry, green. Because CuCl4 2 minus is yellow, isn't it? Plus some blue, green. But the more HCl put in, the more become yellow. Okay, so in the end you get yellow color. Okay, so here you get CuCl4 2 minus, which is yellow color. Okay, or yellowish green, right? Go here. But if you put water, this is HCl. You put water, you go back H2O. Right? But let's say in this case here, right? I put into here ammonia, right? That means that ammonia is going to now fight for the position for a central ion, copper 2 plus. Can ammonia kick up Cl minus 1? Can. Okay. So with time, you will see a deep blue here, a deep blue solution, a deep blue solution of what? Of copper, NH3, 4, and H2O2. Charge is 2 plus. Okay. Copper is on here. So how do you explain? Now remember I told you that the KST must always begin with the aqueous now. So I put the first one here. Okay, now this is the first equation here. Right, this is a KST for copper aqueous 6. Right, it's a blue solution. It's a blue solution. Well, it can come with copper sulfate, copper chloride, doesn't matter. Okay, it's a blue solution. You put ammonia inside, it will replace, it will exchange, it will kick out, it will replace the water here. Actually, go step by step. Kick out 1 water, then 2 water, 3 water, then finally 4 water comes out. Maximum. Okay, it won't go to 6. So it gets on here. Okay, so as you put more inside here, we'll go to inside here. It's a deep blue solution. Okay, right. Of course, you ask for your KST, which they ask you. Okay, stability case that. Okay, you put some here, copper, NH3 bracket 4, and the water must be put down here. Okay, that's part of the complex over, of course, your copper equals another 2 plus, and of course your NH4 power, NH3 power 4. Of course, this is the same lah. Mole minus 4 dm 13. So because the top part cancel each other. So here say, now see this water is not put inside. Okay, no water here, right? Because the water is excess. Same thing this one here. Okay, right? This question came out, just to let you see later. Okay, right? Came out just to cover this other. Okay. So now remember the KST. So when you put the ammonia inside here, they ask you what do you see, right? You can see, of course, first, of course, the yellow color will slowly disappear to form the blue color, because see, as you put ammonia inside here, the second part here, right? This water here will react with your ammonia to form it, right? So as this decreases, you see, isn't it? Decreases happen, it will shift backwards. Right? Shift backwards. So the amount of CuCl4 to minus will decrease, and therefore the yellow color will decrease. Right? It will decrease until all of this is blue color. And then the second part, of course, your ammonia is going to give you your deep blue. So there's a slow change. Right? You can see here, right here. KST for copper tetrachloride is so much smaller than the ammonia. Therefore, ammonia is stronger ligand. Okay, it's the first mark I gave you. As the NH4 is added, the first equilibrium shift to the right, right? So the first equilibrium shift to right here, right? Because why? Ammonia is stronger than water. The water is present while you put your CCl, this one there, because there's still this one here. This is equilibrium. So as it shift to the right, so this one will decrease. Your copper aqueous ion will decrease. So what happened? The equilibrium 2 will shift backwards, okay, right? So removing the free copper hexa aqua from the second equilibrium, which shifts it backwards. So no more of this one is from there, this yellow. So no more. The color of yellow will disappear. And of course, as more ammonia put inside, the first equilibrium will shift to right, will give you the deep blue color of your sun here. Of course, I forgot to put the water. Okay. All right. So this is quite simple, right? Explaining, you can see up here. Okay. Now, I want to show you this here. So now here you can see in this book here, they give you 3, 4 chloride. Remember, this is compared to water. This ammonia also compared to water. 2-hydroxybenzoate also compared to water. 2-dihydroxybenzene also compared to water. Now, the KC always compared originally with water complex. Okay, so you can see that this is a very powerful chelating agent, a very powerful displacement reagent. You will kick out any of this, all this here, right? Can I see here? Right now, even with ammonia, which is very powerfully bonded to copper, can kick it out, okay, to form a square planar, okay. Is a bidentate. Okay. All right. Now we want to go through some calculations first. Let's look at time. Okay, calculations first. Okay, let's look at page. Before we go to the complexes, I will go about into the reactions of copper, all these things like that. But I want to look for this point on calculations of all these complexes. Okay, the first one, of course, being 1, 2, 2. Okay, you can see here. So we go into all these calculations. Right now, here you can see the whole question is on complexes. Right, copper is a transition element of atomic number 19. Okay, 29. Sorry. Complete the electron configuration of copper atom and the copper ion in +2 oxidation state. Okay, quite simple. Okay, if you look at the what I've got here for you. Okay, remember copper is 4s for 3D 10 4s1 because the extra stability of 3D 10. So copper 2+ loss is 1 of 4s and 1 3D9. Okay, so this is very fast. Okay, the following equilibrium exists between the two complexes. All right, for copper ions +2. Remember here. Now this is of course a blue solution. Okay, your blue. So it can come from copper sulfate, no, or copper chloride, no, or copper nitrate. This is just the blue aqueous solution, which is the complex here. This normally comes from HCl, corn HCl. Okay, so here it will kick out the Cl- because it's stronger ligand, it will kick out the water to give you this one here. Now this is octahedral. Octahedral, this is a tetrahedral. Okay, to give you, this is yellow. Okay, name the type of reaction that occurs here. Very simple. You can see here, ligand exchange. The first thing give is exchange. So I tell you, please go for exchange, right? Or ligand replacement, or displacement, or substitution. So, but this is the first word they use. So, learn to cite with temperature. Easier for you. Okay. Okay. So it's ligand exchange. Very simple. State the colors of the two complexes. Of course, it's pale blue. Pale blue. See, all these come out like this. This is yellow. They would accept green, pale greenish yellow. See that here, right? Blue, right? So here yellow or green or green yellow. Up to you. But yellow is the main one because you know why? The blue is the green because of the copper 6 copper 2+ here remaining some behind. Shape, of course, is tetrahedral. Very simple. Okay, so the organic chemistry can score easily once you know your facts, of course. So write the expression for Sally constant for example, so simple. Yeah, but remember you don't put the water. Okay, where's the fella? Yeah. Right here. Don't put the water inside. So which means here got what? Cu Cl4 2 minus, just put that in, don't care, because you can't put 2 brackets there. Don't put the water. Okay, here is Cu, you can put the water here, okay, 2 Cu2 plus, it doesn't matter. 6, okay, these 2 plus are here, okay, and Cl, don't put the 4 here, out here, okay, right, and of course, they ask for units. If you ask for units, you make sure this cancel off, so here, so it's mole 4, right? Remember, -4, sorry, +9. Okay, 3, sorry, 12. 3 times 4 is 12. See, even I make a mistake, don't watch carefully. 12. Okay, because 4. Bunny. Okay. All right, so let's check the marking scheme. See, right? No water, no water, no water, no water. Okay. Okay. Copper also forms the complex ion, of course. Let's see now. Now look carefully. Here they put 2. I blew it up for you. See, I told you it don't have to be 4. See, here is 2, isn't it? Right? Because I told you the ammonia comes out 1 at a time, depending on the concentration of ammonia used. But the final one will be CuNH3 bracket 4. That's the final one. But it can come out 1 by 1. So here come out only 2. Can come 3 also. Later you see the color changes a bit. Okay? So don't be surprised if you use NH3 2. Okay? I said, oh, Mr. I say always NH3 4. Not necessary. I tell you now, okay? Be a dumb head, okay? That's 4 here. Remember, it's 6, 2 plus 4 is 6, so octahedral. So always make sure it's got the water here, right? Because En is a bidentate, right? So bidentate is 2 already, 4, 6, okay? En is a bidentate ligand of ethane, 1, 2 diene, okay, blah, blah. And then here's first equation, right? Here, of course, remember, no, it's like they always start with what? Water. With the water ligand, right? Always, the KST always refer to water one. Okay, here's the one here. What is meant by a term by ligand? I told you, 2 marks in it, right? Remember, you always say, there's the molecule that has 2 pairs of low electrons that form 2 dative bonds with a central atom, 3 points here. Bincangkan. Okay. See here. Species contains 2 lone pairs. Sometimes only it's 1 mark, no, 2 lone pairs. They each form a dative bond or form 2 dative bond. Okay, this mark. See 2, they break it up to ion or atom. There are 3 points here, my dear friends. Please write the 3 points. So don't get how many marks they gave. All right. Sometimes they write these 2 only 1 mark, no. All right. I don't know how they're going to change the marking scheme. You better give all these 3 things, okay? Lone pairs from dative bonds with central atom or ion. Basically, can't do that. I think you better go and do B levels. Okay? Identity. Now here give you the Kstab. Okay? The table lists the values of stable constant for 2 complex scale. Remember, this one here is relationship to the water. No, compared to water with the CuH2O6. Again, always compare with the water one. It means the starting point is water. Same thing here. Okay, so these 2 things, of course, the En is more stable than your ammonia, isn't it? Yeah. So the value here, 10 and 7. Okay, so what do these Kstab values tell us about the relative position of something here? Okay, that means for 2, right, is shift more to the product side. How do you explain it? How do you give that an answer? Okay, right. See, equivalent to lies more to the right hand side. Equivalent to lies more to the product side, or favors the forward direction because bigger value. So favors more products being formed. That's all they want. So see what they ask, see what they want. Okay, what they ask? Tell us about the relative positions of the stability constant. That means 1 and 2. 1 and 2. So 2 will the positions lie more to the right hand side or lie more to the products, which means more products are formed, right? Or En is a more stable ligand than your NH3. But they say position lie more to the right hand side. Okay, right hand side means the products. If you're not sure, just put there lie more to the product side. Okay. All right, now here we won't go now, okay? We've done before, okay? Another question here, 132. We just want to fix ourselves on the calculation, okay? Right, 132. I want to finish all this. Prepare. New Year, man, holiday. My goodness, prepare for you fellas. Okay, cadmium, all right? Cadmium is a dangerous metal found in where your batteries, man. My goodness. All the companies that make batteries, they throw all these waste products into the river, and you and I drink. Happy, yeah? Okay, cadmium ions form complexes with primary amines. Okay, primary amines. Remember, R and H2. Okay, and 1,2 diamine. It 2 fellow here, and of course your En. This remember your En. Okay. All right, NH2. Okay, these are secondary, not secondary. This is diamine. Okay, 2 here because 2 here. Okay, first equilibrium 1 they put down for you. Okay, see 6 here, 10 here. Of course, more dentate. Well, stronger ligands there, stronger replacement power, stronger exchange power. So this one is the first one. It's 4, 2. Of course, here they didn't tell you whether it is a square planar or a tetrahedral. Don't care. Okay, normally these big fellas are all square planar. Write the expression for a stability constant for one state. Okay, it's state units here. So 2 marks here. Obviously, remember here got no water, so we don't have to worry. So be what? CD, CH3, and H2 bracket 4. Okay, 2 plus here. Just put brackets here, okay? Right? Don't put bracket. Always I tell you, too many brackets. Crazy. CD 2 plus. No? So don't put the water there, don't care. Right? The 2 here is for the bracket, you know? Bracket, right? H2, write the whole thing. You don't write the whole thing. Okay, bracket 2. Okay, it's this, right? Remember here is 1 cancel everything. So it's 2, isn't it? Right? So it's what? Mole square dm square of it, what? This minus 6. Let's check the answer. I didn't put that down. Never mind. I can't go back. Otherwise, I see my face again. Come on, I didn't put I'm an idiot. Never mind. Okay. Right. We'll get there. Right. Quite simple. Okay. It's quite simple. Okay. Right. I tell you what, I will stop for a while. I'll get them because this is important. I actually done it already. Okay, pause recording. Actually, I got it here. I forgot. Okay, it's just at the end here. Okay, you can see this cadmium here. Remember, it's the last part here. Okay, remember that this one here. Mole power minus 2.6 is the last part here. I forgot. See now. Okay, minus 4. Minus 4, is it minus 4? Oh, sorry. I see, I didn't check. So I thought it was this equivalent 2, it's equivalent 1. So this is wrong, isn't it? Sorry, guys. See, I make a mistake. So you better be careful. Lousy teacher. Okay, CH3 and H2 bracket 4. That's right. So I'm wrong. So can I be a teacher? So somebody to teach you. I don't teach you. Okay, here of course is cancel here. Here's 4. So it's 4 here. All right. So 4 times 3 is 12. So this will be your answer, 4 and 12. Okay. Right. 1 mark each. Yeah. So you can see the marking scheme here. 1 mark each. Okay. Right. And this one is quite tricky. Okay. It's quite tricky. So you see here. Okay. Poisonous. Cadmium ion is poisonous and need to be removed from some water supplies. This often is done by a complexing agent, which means the agent will complex it and form a heavy, soft, you will precipitate it and filter it out. Okay. So the complexing agent, the complex is actually solid now. So can filter it out, so can remove the cadmium out. The groundwater has a concentration of cadmium as this small amount. Okay, 10 minus 0.123 and 1 here. Now 4 isn't it? 4 is 1, 2, 3, 4. Okay, so it's 3 here. Now you need to know this. You be better be sure. Current concentration of your complexing agent. This is a complexing agent. Okay? It's called a complexing agent. Okay, the ligand. You need to reduce concentration by a factor of 1,000. That means this one here times 1,000, which is equals to remove this by 1, 2, 3. Okay, so we have 1, 2, 3. Okay, this is actually 4 minus 4. This times minus 3. So a total of 1 times 10 to the power minus 7. Okay, that means go from here to here, from here to here. Right? So in this direction, blah blah by 1,000. Okay, so calculate here. So of course you start with this whole thing here. Now let me show you how this one here. Okay, cadmium. We do slowly. Okay, cadmium CD 2 plus your CH3 You need to know step by step because sometimes the numbers are quite tricky. That's all. It's 4 NH3, okay, goes to what? CD, CH3, NH3, bracket 4, 2 plus. Now, if you're not sure, go and check the equation again. The equation is free, given to you. Okay, yep, the KST is right here. It's good to put that here, 3.6, KST, Kstab, 3.6, 10 to the power of, I think it's minus 6. Yeah, oh, 6, not minus 6, 6. That means you form a 1. Okay, now, time 0, initial. How much was present? This one was present. Okay, so it's 1 times 10 to the power of minus 4 moles per m cube. Okay, okay, right now at equilibrium, T equilibrium, how much is supposed to be present? Present at equilibrium, present. This is 1 times 10 to the power of minus 4 or 1000. Okay, right, which is equal to 1 times 10 to the power of minus 7. You bring out this up, 1 times 10 to the power of minus 4 and 10 to the power of minus 3 there. So 7. So how much is this? It is actually 0.60, 1, 2, 3, 4, 5, 6, and 1 here. So this is the final one. Okay? Right? Okay, it's the final one. Well, how much of this added? We'll put y, x. Okay, this is y here. All right. Now, how much reacted? Okay, original 1 times 10 to the power of minus 4, right, minus 1 times 10 to the power of minus 7, which is 0.1231 minus 0.123456. Now this is maths. I tell you, you need to go down to basic maths to find out actually. Okay, so minus for me, 0.1231 minus 0.123456. Okay, put 0 here. This 0, 0 here, 0 here, 0 here. So it's 9990000 point. So it's actually 1, 2, 3, 4, 5. So 9.99 times 10 to the power of minus 5, is it? Reacted. Okay? Or how much reacted? You can put it as well. It can be 10 times, this is about 10, and to the power of minus 4, is it not? Yeah, no. Okay. So this will be here. So how much reacted is here? How much present here? The reactor is what? 10. Okay? Right? So 10. Okay. Yeah, this 5. See, even I make mistakes. So it's 1 times 10 to the power of minus 4. Okay. So it's 1 times 10 to the minus 4. Easier. So this is what? This is your, what is present is not here. Okay? Right? 1 times 10 to the power of minus 7. And this is y you put inside. Okay? So KST B is equal to concentration of CD, CH3, NH3, bracket 4, power 2 plus over CD 2 plus CH3, NH3, power 4. So it's 3.6 times 10 to the power minus, I think it's 6 now, sorry. 6 there, okay. It's equals to, this one is how much? This is it. 1 times 10 to the power of minus 4. Okay now. This is the one present in. Well, let's write the formula. Over. Okay, the amount left behind, how much is? 1 times 10 to the power of minus 7. And y power of 4. So you can solve it, can't you? Right? So y power of 4 equals to, you bring up here, bring this down here. 1 times 10 to the power of minus 4 over 3.6 times 10 to the power of 6. Okay? So here, times 1 times 10 to the power of minus 7. Of course, you quadruple root here, root 4 here. Y equals to root power 4. 1 times 10 to the power minus 4 over 3.6 times 10 to the power 6. Maths a lot of maths, so be careful, your calculator. Minus 7. Now I'm just going to give you the marking scheme. I'm going to solve for this. Okay. Right, see ya. Okay, start. Equilibrium is not. Okay. So this is the amount, well, the amount reacted will be how much? Reacted, did you put here? Reacted, how much reacted? Because reacted with the amount form, is it? Right? Will be 1 times, well, here, this further here, so 10, I think so. 1 times 10 to the power minus 4 minus 1 times 10 to the power minus 7. Remember that? So I told you it's about, right? It's about actually 1 times 10 to the power minus 4. Because all precipitated already. Because if you work it out like I did 1, 2, 3, 1, yeah, it's minus 1, 0.1, 2, 3, 4, 5, 6, 1. So it minuses, okay, 0.001. I do it again for you lah. 0.1, 2, 3, 4, 5, 6. Remember? Here got 2 more zeros. Yeah, 3 zeros here, 2 more zeros here. Yeah. Is it true now? 1, 2, 3, 4, 5, 6, 1 here. Okay? 6 zeros here, so 0 here. So it's 9, 9, 9, 1, 2, 3, 4. Right? So actually it is 1, 2, 3, 4, 5, 6. Okay, or 1, 2, 3, 4, 5. 9.99 10 to the power of minus 5 is approximately equals to 10 times, in fact, all same as the first one, is it? Same as the first one here. So we can use this one here. Okay, this is the one here. So this is the amount of this further here. Okay, right? Okay, so I put 999 or whatever up to you, right? It doesn't really matter. Okay, so you can work it out. See, either use this one here or this one here, right? So you can see root 4 and this answer here. So 0.129 or 0.13. All right. So it's the answer here. Okay. Okay. 0.129. Work it out and see. All right. So this is how you do it. Remember, they say diluted by a factor to this solution by a factor of 1,000 means 1 over 1,000. The factor is. Okay. Now let's look at another one. 134. Because I've got about 15 more minutes. I'm going to do a few more. 134. Give you all the types of reaction that there's here. 134 down here. Okay, here. Hexa, aqua, iron 3. Hexa means 6. Aqua means water. Iron 3 means Fe3 plus. Violet, pure violet, pale violet, not pure violet, pale violet. Okay, like a purplish color. They tell you the color. They form a color solution with fluoride ions in equilibrium 1 here. They will kick out only 1 water. Okay. 5 remain. This is about 5. Okay. Violet to colorless. Then now, this, as I said, always refer to the aqueous water as a starting point. Remember this. Cyanide, this is the famous reaction for iron 3 in your SPM or IGCSE. It's a real test for iron 3 plus. You put potassium cyanide inside here, get a deep red or get a blood red color. It's a very beautiful, deep red color. Sure test for Fe3 plus. Okay, go inside, you kick 1 again. Okay, now this is only 1, okay? 1 to 5, 1 to 5, okay? This is 3. Okay, so there are 2 equilibrium here. Predict and explain the sequence of color changes you will observe in each of the following experiments. Okay, so now here, all right, a few drops of K potassium is on here. Is potassium thiocyanide. Okay, added to aqueous, followed by a few drops of this on here. Now when you put this on here, when you put this in, let's say got here. Okay, here of course is your original FeH2. Or you don't know how to draw the diagrams. This violet, pale violet. Okay, now you put some of your KSCN inside here. Of course, it will turn to what? Deep red, huh? Right? So it forms to deep red, which is your FeH2O5 SCN 2 positive. Okay, so you turn to the pale violet solution turns to deep red solution. Right? When what? When KSCN added, followed by a few drops of KF. KF, remember all potassium PS source absorbers, so you give you what? K plus and what? F minus. This is where it come in. Okay, and of course now this is stronger now, right? 5, isn't it? So then when KF added, what happened? It will kick out the SCN. It will turn to what? Turn TURN of TH1. It will turn to what? To colorless. Yeah. Okay, I see the answer. I think it's here, if I'm not mistaken. Hope so. I don't know what happened. Okay. See, the sun was here. I don't know how come I didn't see it, no? Okay, here you are. Remember? All right. Is it here? Wait, I have to. Okay, I got it here. Right? Remember, they say here. All right. They say here, pale violet. Now, because see, all this happens, these two things happen. Maybe I go to it again. Right? If a few drops of KF will drop to this one here. If this is one here is your F H2O 6 and 3 plus. If I add in here your KF, okay, of course, the pale violet will turn to colorless. Right? Before for a few drops down here, so to colorless. Why colorless? Because FeH2O5 and F, right? 2 plus here. But you put then later your KSCN, no color, no change, because why? Your fluoride here is stronger ligand than your SCN. See, stronger 5 and 3. So you got to say, right, for both of them, right, colorless, and then with KSCN remains colorless. Now you have to give your rationale, okay? Which means who is stronger ligand? So the Fe, the F minus is stronger than your SCN is stronger than water as a ligand. Okay, right? What direction is this? Ligand exchange, right? Okay, you see this here. I got it here just now. I don't know what's wrong with me. Okay, all right. You can see here. They put here one mark here is mark. Kstab. All right, this one here is stronger than this, stronger than this one here, or this one here. I can say so. See what I put here is well not very good. Okay, I can put here Kstab. Kstab for what? For Fe H2O5F stronger than Kstab Fe H2O SCN. Okay, get up. This one here. Okay, so the mark is given. This one here. Okay, right. So you can see here how they put the thing here, the Kstab. Okay. Of course, they always refer to, as I said, the water here. So if you put the water here, it's not wrong. Observation: violet to deep red and deep red to colors, 1 mark. Okay. Violet to colors, okay, stay colors, 1 mark. Okay. So essential mark is, well, 4 marks. I don't know how to give the marks. Okay. 1, 2, 3, and 1 for overall change. Ligand displacement, ligand exchange. Okay. Either way you can put it. Okay. I got 5 or 10 minutes more. I want to go on to a few more questions. Okay. This is 134. So let's look at the 138. Oh, 138. About same on 138. Okay. All right, now here again, right? Just give you the whole range of things you can see for yourself. Iron 3 complexes separation. Get iron 3 here, right? The blood red filler here. Okay, the blood red filler here. I want and 2 here. Okay, current 1, current 2. All right. Right expression for example, it's very simple, isn't it? So of course this will be what? FeSCN. Now they didn't put the water, so don't care. You copy as it is. Of course, actually there's a H2O5 there, but don't care. 2 positive over what? Over Fe. Of course, got 6 water here, but don't care. You do as they tell you here. SCN minus. So 1 minus 1 is small. Minus 1 DM3. It's not. So here is where we are. Constant of FeCl4 minus over what? Fe 3 plus and your Cl minus and 4 here. That's not. Yep. So don't care what the water don't put in our mind. So this one cancel off. So it will be mole minus 4 DM12. Okay. Let's hope I got this here. What year is this? 17. I think here. Okay, it should be here. Now I don't know what happened to me. Okay, I can't find again. I'll kill myself. Here. Okay, now. Okay, see? All right, so they don't put the water, guys. Okay, see here. Okay, right? Okay, so easy to get a mark, isn't it? 3 marks, 1 mark for each one, 1 mark for the unit. This one here is a bit tricky. All is a maths, no. Here is all maths. I'll show you, right? So they ask you now, right expression in this case here, right? And the equipment can set up between these two combinations shown here. So equipment 3 is a mixture of both, you know, right? Fe, if you put FeCl4 here plus SCN here, they will replace, right? This one will kick out the chlorine because this SCN is stronger than chloride ion here to give you this one here. Okay, so there's an equilibrium here. So, well, will it kick out completely or partially? I don't know. So you got it here and you can find out. Okay, so the right expression for equilibrium 3 in terms of Kstab 1, Kstab 2. So what you do is, of course, I'm going to put over here. Okay. Hopefully the space is enough. Let's see how to get the space over there. Never mind. I'll rub all these parts here. Okay, this one we did the data. Okay. I did it in a bit of paper, but I should have done it here earlier. I'm so sorry. I wasted time. Never mind. At least we can see the whole working, okay? All right. There are 2 ways to do it. One, of course, is to substitute. One is to equate the 2 values here. Now, I put it smaller, okay? All right, so can write more. Now, for this one here, all right, in blue, so it's easier to see. For this one here, right? So the K stability 3 is not. Is equals to what? Concentration of FeSCN bracket is 2 plus, and your Cl minus 4 is over FeCl4 minus bracket SCN. It's not. Yep. So now I got these two here to play with, these two here to play with here, to put inside here. Very simple. Now look at this one here. Now this, I'm going to put red color here. Okay. See this part. This part is actually this part. Is it? Yeah. Okay. So you put this up here, right? You put this up here, you get K step. It's all substitution, it's all mathematics. Okay. Equals to K step 1 times Fe3 plus over. Now look carefully. I'm going to put green color so you can see clearly. Okay. This part here, FeCl and Cl minus 4. Whoa. Okay, here. It's actually this part here. Whoa. No. So it's actually K step 2. Huh? Because you bring this up here. Yeah. So we're under here. So it's K step 2. The Fe will cancel off. Okay. So K step 3 is equals to K step 1 over K step 2. Oh my God, the fucking scheme here for your sake. 17 May, June here. Okay, I don't want them here. The next one here. K step, idea. K step 1 over K step 2. Okay, K step 1. K step, where is the gundu? Okay, K step 1 over K step 2. Okay. Numerical values for this stability constant are shown, blah, blah, blah. So what is K step 3 equals to? K step 1 is here 1.4 times 10 to the power of 2 over 8.0 10 to the power of minus 2. Right? You can solve this to make it easier. I want to solve this. Is equals to here 1750. Okay, 1750. And what units? No units. Unit. Oh, units. Got units, sorry. This one here. Okay. K step 1, what's the unit? K step mole minus 1 dm3. K step 2, mole minus 4 dm12. So it's going to cancel 3, isn't it? So it's mole, mole 3. Here's dm minus, bring out here 3, 9. So this one here. Okay, so it times up already. Okay, yeah, all right. So it's 139. There are a few more. I'm sure you can do all by yourself. Okay, so now this is how the K stability comes out. Just let me show you a couple of those things. Okay, 141. You can try yourself. Okay, here we are. 141. See now. Same thing, K step 1, K step 2, and ask you to, okay, right, okay, put K step 3, okay. So one more, 156, past 156, you can see. Now all these questions we'll do later, okay. One here. Now this is interesting. EDTA, okay. I'll spend about a few more minutes here, okay. Now, EDTA is a polydentate of ligand, which is a solution of EDTA. Okay, minus 4 added to a solution containing copper 2 plus. Okay, a new complex is formed and it's the first EDTA. Why? Because EDTA has got what? Has got 6 donor atoms. Okay, that means it can form octahedral, isn't it? Form octahedral. What with copper 2 plus. Okay, so of course the name direction of course ligand what? Exchange. What else? Okay, expression very simple. Now remember here they give you not, they give you. So it's of course here. Remember you put on copper 2 plus EDTA give you what? Copper 1 to 1, right? Bracket EDTA. Okay. This whole thing is what? Is minus 4 plus 2 is minus 2 over. Okay. So your KSTAB is equals to copper EDTA, what charge? Minus 2 over copper 2 plus and EDTA. Okay, milk value for this is this one. Okay, right? Okay, this value here tells us about this one, which means it's a very strong completing agent. That means the equivalent will shift all to the right, isn't it? Okay, now let's see what the marking scheme is. I think I got it here. 18 May, June are here. Okay, okay, EDTA, okay, see? Right? Sorry here. Okay, I'm sorry, I take a bit more time, okay? So EDTA, so more stable than the one here. The compound is more stable than water. Of course, comparatively, okay? A few ways you can put it, okay? You want more stable than your water complex here. So here is that, right? So here, there's the gundu, right? So, okay. This complex is more stable than your copper. Remember, you always compare with the aqueous copper, you know? Okay? 2 plus. So big. That means it will complex oil and it will buangkan. No, that's why EDTA is used a lot for flocculation, for cleaning water, you know? Because it will float on top as a scum and you chuck it out. Okay, I finished all this part here, and next time I'll talk. There are 3 parts actually I have in mind. One, of course, is the chemistry of copper 2 plus, cobalt 2 plus, and nickel 2 plus. Next, of course, is the color, and lastly, of course, is for paper 5 one to form the stoichiometry. All right, so I'll see you next time here. I'm trying to find the button for stop. Stop. Okay, bye bye.